All right, we're gonna cover section 9.4 today, and that is on polar coordinates. So let's go ahead and do that. So the idea is in the polar coordinate system, again, let me take a step back. What we did with parametric equations and the calculus with parametric equations is we created another system that we can utilize to do calculus. And sometimes the calculus in that parametric system is easier to do, or is just more beneficial to do in that system than it is in our rectangular system. Well, another system that we can look at is the polar coordinate system. And normally, when we get rectangular coordinates, we have left-right direction, that's the XY direction, and left, right, and up, down. So regular rectangular coordinates, we get all these points X, Y. Well, with polar coordinates, what we do is we judge a point by the distance it is away from the origin and the direction from what we used to call the x-axis, but we'll call the polar axis here. And so if you give the r and the theta, then you're able to get to any point you'd like. Now, when we actually create and do transitions from rectangular to polar or from polar to rectangular, it's actually just a right triangle on the grid that gives us all the information that we need. And when we're doing coordinate conversions back and forth, we're going to essentially use the Pythagorean theorem and SOHCAHTOA on a right triangle. If you remember SOHCAHTOA, that meant sine of an angle is the opposite over the hypotenuse. The cosine of the angle is the adjacent over the hypotenuse. And the tangent of the angle is the opposite over the adjacent. Those are going to give that idea gives us what we need to know. So let's take a look at what I mean by that. And let's say I have a point in the plane. Now, if we're doing rectangular coordinates, that point is going to be measured by a distance from the origin, how far to the right, and how far up I go. And the amount to the right or left I go is the x value. The distance up is the y value. So the rectangular point is going to be x comma y. What the polar point does to get to the same exact spot, what we would do is we measure the r. We call that r for radius because when you think about all points of length r, they create a circle. All right. All points with the same R create a circle. And then we say the other thing we need is the angle from this axis. This is called rectangular. This is called the x-axis in rectangular. But it's also called the polar axis when we're dealing with polar coordinates. And so the point in polar is r comma theta. It's the distance you have to travel and the angle from this polar axis or x-axis. Okay. Now, this is a right triangle. This forms a right triangle. And so we get all of the nice things that we know from a right triangle. For instance, the Pythagorean theorem says that hypotenuse squared is equal to x squared plus y squared. So length of the hypotenuse squared is equal to the base of one leg squared plus the base of the other leg squared, or the length of the other leg squared. So these two things squared become r squared. We also have our SOHCAHTOA. This is what I was saying earlier. The SOH part says that the sine of an angle, and obviously we're going to use this angle, sine of theta is equal to opposite, that's y, over hypotenuse, that's r. The CAH part of SOHCAHTOA says that cosine of the angle, and again, we're going to use that angle, is the adjacent, which is x, over the hypotenuse, which is r. And then the TOA part of SOHCAHTOA says that the tangent of the angle is equal to opposite, which is y, divided by the adjacent, which is x. So those four features from a right triangle actually determine how we are going to be able to convert back and forth between polar and rectangular. Okay. One thing I do want to state is that this all makes a lot of sense in the first quadrant. All right. One thing you have to watch out for a little bit is if my point is not in the first quadrant, let's say my point is over here. Yeah, let's do that way. The angle that we're going to want is still going to be the angle from the polar axis. So the theta is actually going to be this angle. Some people think it's going to be this angle in here. It's the angle from the polar axis. So you have to be a little bit careful about that. And the same thing with third quadrant or fourth quadrant. All right. So don't think that the inner angle is that one. But still, all of the same stuff is going to work out just fine. So we're going to use these properties of the right triangle to do conversions back and forth between rectangular and polar coordinate systems. And we kind of clean these up a little bit. Usually, these things are written in a slightly different manner. Conversions, let's start here or here. Let's start actually here. If I multiply both sides of this equation by r, that leaves just x on this one side. And then r cosine theta on the other. So I just multiply both sides by r, canceled the r out here. So x is r cosine theta. If I do the same thing over here, multiply it by r, I see that y is equal to r sine theta. And then I have these two. R squared is equal to x squared plus y squared. Usually, when we do conversions, we just leave it that way rather than writing square root. And usually on the tangent of theta, you write that as just y over x. Now, the reason I'm writing them like this is because notice that if we start with polar, if we start with the r and the theta, and we want to convert to the x and the y, then these two equations do that really quickly. If I start with the x and the y, and I want to get to r and to theta, then these two equations do that fairly quickly. All right. And that's basically what this slide says, this next slide. It says if we have rectangular coordinates and we want to go to polar, or if we want to go from polar to rectangular, there are 4 different conversion equations. You saw where the origins are, like where they come from. The first two, x equals r cosine theta and y equals r sine theta, are really good to go from polar to rectangular. The other two, r squared equals x squared plus y squared, and tangent of theta equals y over x, those are really good to go the other way. And that's what we're going to be doing in the first part of this section. All right. So here we have some polar points, 8 pi over 2. -7 pi over 6. -8, 3 pi over 2. And then 0 pi over 4. I might do another as well. There's a lot of... Let's do 5 pi over 4 too, I guess. So I'm writing all those down on the board, and I'm going to do a conversion from polar to rectangular points. So here are my polar points. Let's talk about the corresponding rectangular. Well, what I would do is I would say 8 pi over 2. That's the r, that's the theta. So x is simply 8 times cosine of pi over 2. And y is 8 times sine of pi over 2. I can type those into my calculator. Again, make sure your calculator is in radian mode when you're dealing with calculus and angle measurements. You always want to be using radians to get our standard, things, and we're going to be dealing with calculus here. So 8 times cosine of pi over 2 is 0. 8 times sine of pi over 2 is 8. If you think about that, it should all make sense. An angle from this polar axis of pi over 2, well, that's an angle that goes straight up, and we're going 8 units straight up. By the way, that's right along the y-axis, right? What we normally call the y-axis. A lot of times in polar, the y-axis is called the line theta equals pi over 2 because that aligns with the y-axis, all right? The x-axis is called the polar axis. And the line theta equals pi over 2 is the y-axis. All right? So we're going to see that later, probably next time, where we rotate something around the polar axis, or we rotate something around the line theta equals pi over 2, and you'll see that just means x-axis, y-axis. All right, let's do another. So notice how quickly this can go. 4 times cosine of negative 7 pi over 6. 4 times sine of negative 7 pi over 6. I'm going to be able to type that in. This time, it's not going to give me a nice whole number like 0, 8, but we can still do it. I get negative 3.46 for my x values. And then a 2 exactly for my y value. Okay. By the way, negative 7 pi over 6, that's an angle that's negative. So we're going to be traveling clockwise from the polar axis. Negative 7 pi over 6 shoots over in this direction somewhere. So you're getting a point over here, which makes sense that the x value would be negative, the y value would be positive. We're going left and up. Negative 8 3 pi over 2. This also gives me 0.8. If you think about what this does, the angle 3 pi over 2 is pointing downward, but using a negative r instead of a positive r shoots me back the opposite direction. So using a negative r shoots us back the opposite direction of where the angle's pointing. Okay. A lot of times when we do our conversions, the other way, we'll assume we have positive r's. So we all have the same point. 0 pi over 4. X equals r cosine theta. Y equals r sine theta. Since the r is 0, we're at the origin. Anytime r is 0, we haven't left the origin, right? And it doesn't matter what angle we're at because we haven't traveled at any distance. So anytime r is 0, we're at the origin. By the way, sometimes it's called the pole at in some situations. So let's do the last one. 5 times the cosine of pi over 4, comma 5 times the sine of pi over 4. Again, r cosine theta gives me the x value. R sine theta gives me the y value. And if you do that, you end up with about 3.54 for both entries. That pi over 4 shoots off at the 45-degree angle. And if you think about what the 45-degree angle does, it always gives you the same x and y values. 45 from the origin. So the angle of pi over 4 gives you that. So that's going from polar to rectangular. And the calculations are pretty straightforward. You plug it into your calculator. Again, I'm trying to explain this as I go, explain why things are the way they are. But essentially, all we have to use is the fact that x is equal to r times cosine theta and y is equal to r times sine theta. And just plug in the r and the theta, and we're good to go. Okay. There's a little bit more to it with going the other way, using these other two equations. I'll explain that here. So let's go from rectangular points to polar points. Okay. So we have points like 2, 2, -3, 4, -1, √3, and 4, -2. That's good enough. We're gonna leave some space here. All right. So one of the things that I have to worry about with polar is, first off, because we have r squared equals x squared plus y squared, technically r could be positive or negative, okay? So in our class, in this class, we're just going to always use positive r's. All right? So we use positive r's. When we figure that out. The other thing is this. Let's say we're at the point 2, 2, for instance, in rectangular. What angle do we have? And I'm going to spoil it. It's going to be the angle pi over 4. Angle pi over 4 gives me that line. But if we're at pi over 4 and we add 2 pi to that, so 2 pi plus pi over 4, we're at the same point. So there's actually a bunch of different angles to choose from. And so we have to also limit our angles. We're going to limit our angles between negative pi over 2 and 3 pi over 2. There's a reason, so we're going to use positive r's, and we're going to take our theta between negative pi over 2 and 3 pi over 2. The reason we do that is because based off of our inverse tangent. And again, I'll show you that in just a second. All right. I'm just making sure something. Yeah. So we use positive r and our angle between negative pi over 2 and 3 pi over 2. All right, so now we're ready to go. So now we have the rectangular point 2, 2. To get the r, we solve this equation for r by plugging in 2, 2 into the xy values. All right. Now, actually, I'm just going to round that. That's going to be square root of 8. So it's not going to work out real nice, but square root of 8 becomes 2.83 roughly. So that's what I'm going to have for my r value in the polar coordinate version of this point. For my theta, I'm going to make a note that this is in the first quadrant. So since tangent of theta is equal to y over x, the theta that I'm going to get is going to be inverse tangent of 2 over 2. So I do inverse tangent on my calculator of 2 over 2, and I get 0.7854 for my theta. Theta is actually equal to pi over 4, which is that approximate value of basically 0.79. So that's my polar point. That's my polar point. Now, the reason I noted that that was in quadrant 1 is that inverse tangent of whatever always gives me back values in quadrant 4 or quadrant 1. In other words, it gives me back values where the theta is in this section. All right. So what happens if my point is in quadrant 2 or quadrant 3? And it just so happens the next point, -3, 4, is in quadrant 2. Well, the angle that we're going to get back, we're going to see, is actually this one. That shoots in the opposite direction of what takes me to -3, 4. So what we're going to do, since inverse tan gives us back a point in quadrant 4, and we actually have a point in quadrant 2, we're simply going to add pi to the angle. So if a point is in quadrant 1 or 4, then what we do is we say the angle is simply tangent inverse of y over x, whatever that is on my calculator. But if the point is in quadrants 2 or 3, then what we do to find our angle is we take tangent inverse of y over x, and then we simply add pi to it so that it goes in the exact opposite direction. So tangent inverse plus pi. So let's do -3, 4. I'm going to use the same stuff we had before. R squared is equal to x squared plus y squared. R is going to be the positive square root of -3 squared plus 4 squared. That gives me 5, pretty sure. Make sure, definitely I got it, but yeah, it gives me an R of 5. So the polar coordinate's going to have an R value of 5 here. The point is in quadrant 2. So when we have the fact that the tangent of theta is equal to y over x, what we need to do to get theta is take tangent inverse of 4 over -3 and then add pi to it. I better understand why we have to do this, because if somebody said, well, actually, I wanted 3 -4, when you do tangent inverse of 4 over -3, that's the exact same value as tangent inverse of -4 over +3. And so one of these is shooting off into the quadrant 4. One of those is shooting off into quadrant 2. My calculator on the tangent inverse always shoots me into quadrant 4 or quadrant 1. And so if I want quadrant 2 or quadrant 3, then I have to add pi to it. So that's all I do. Tangent inverse of 4 over -3 plus pi gives me about 2.21. So about 2.21 radians. Go ahead and take a minute to try these last two conversions. Convert the point -1 square root of 3 into polar, and convert the point 4 -2 into polar. All right, let me go through these. So first off, I like to start by finding the R. And remember, we're always using positive R values. Okay, so R is going to be the square root, the positive square root of x squared, that's -1 squared, plus y squared, that's √3 squared. And when you calculate that, you get 1 plus 3, that's 4, underneath the square root. So you get a 2 for your R value. So an R value of 2 in that case. Now, what's the angle? Well, because this is in quadrant 2, because -1 √3 is in quadrant 2, we have to do the thing where when you take tangent inverse of y over x, √3 over -1, then we add pi to it. When you do that, you get approximately, I forget which one. Yeah, 2.09 as the amount of radians. Your radian measurement from your polar axis. By the way, this is why we write the conversion equation like this instead of writing it with tangent inverse. Because if you wrote it as tangent inverse, then you'd have to only be dealing with the first and fourth quadrant. Writing it like this makes it true for all 4 quadrants. But then when you try to solve for theta, you have to know which quadrant you're in. Quadrant 1 and 4, you just use tangent inverse. Quadrants 2 and 3, use tangent inverse plus pi. Let's look at the last point there. The last point is 4, -2. So R is going to be the square root of 4 squared plus -2 squared. That's the square root of 20, which is 4.47 roughly. So that's the R value. 4, -2. 4, -2 is down here in quadrant 4. So we're in quadrant 4. That means to find the angle theta, we just have to take the tangent inverse of -2 over 4. Remember, y over x. And when you do that, you get approximately -0.46, which again should all make sense. If you're an angle, you go -0.46, you should be pointing in that basic direction into the 4th quadrant. And that's it. So that's the conversion from rectangular to polar. Okay. Ooh. Hit the wrong button. All right, and by the way, on Moodle homework, it'll say the exact same thing. Use a positive R value and use your angle between -pi/2 and 3 pi/2. okay? And on the test, it'll say the same thing. Use positive R value and make sure your angle is between negative pi over 2 and 3 pi over 2. Now that we've converted points, now we're going to go back and forth between rectangular equations and polar equations. And like I said, some rectangular equations are harder to deal with. Some polar equations will be easier to deal with. Let's take a look at this example. In this example, we want to convert rectangular to polar. Now, we're going to use the exact same tools that we previously have. So when I say the exact same tools, I mean these four equations. X equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, tangent theta equals y over x. Okay. Whenever you're going from rectangular to polar, you can always, by default, substitute every x with an r cosine theta and every y with an r sine theta, and then simplify. But also, you see that if we ever have x squared plus y squared, we can replace that with an r squared. Also, if we ever have y over x, I can replace that with a tangent of theta. So in this one, the most efficient way is not going to be replacing each x with r cosine theta and each y with r sine theta. The most efficient way is going to be noticing that x squared plus y squared can all be replaced with r squared. So I take x squared plus y squared, and I replace that with r squared. And then if you're willing to use just positive r's, then we get r equals 5, if I'm willing to use just positive r's. By the way, notice that x squared plus y squared equals 25. That is a circle of radius 5 centered at the origin. That circle of radius 5 I didn't draw that very well, but is what you get with r equals. All right. So r equals stuff is just circles centered at the origin. So what would r equal 1 look like? R equal 1 would be just a circle, radius 1. R equals 2, I didn't draw this to scale, but you can see that you're just getting, I didn't draw that very well, but just getting a bunch of circles with r equals, okay? And if you look at the graph of a polar grid graph paper often starts with a bunch of circles of different radius. That's because r equals 5 creates, or r equals numbers create those circles centered at the origin. Okay. Let me see something real quick. Oh. Yeah. Sorry. Let's look at this one. Y equals 3 times x minus 2. So that's a pretty standard line. Y equals mx plus b. And we want to convert that into polar. Well, in this case, I don't have, a y over x that I can mess with tangent. I don't have a x squared plus y squared. So when in doubt, just replace every x we see with our cosine theta and every y we see with our sine theta. And that's what we'll do right here. Replace the y with r times sine theta. Replace the x with r times cosine of theta. Now, this is a little bit of an aside, but when we graph rectangular equations, a lot of times we put them into function form. So we have y equals an expression in x. Well, in polar, oftentimes when you put polar into function form, you go r is equal to an expression in theta. So just like we solve like a line, we have y on one side. A lot of times in polar form, they'll solve and they'll put the r on one side. So that's what I'm going to do here. Just kind of like we had over here, we had r on one side equaling an expression. I'm going to solve for r on this one. If you do that, you'd subtract 3r cosine theta from both sides. That would give you r sine theta minus 3r times cosine theta equals -2. And then I'd factor out this r. And then this number, I would divide both sides by that number. I'm not going to write that. I'm just going to write the answer. -2 over sine theta minus 3 times cosine theta. So r is equal to an expression with thetas in it. Now, these two examples side by side, where we've converted rectangular to polar, kind of show you the nice thing about being able to use both systems. All right? If I were to try to solve this and do things like take derivatives on a circle, it's actually kind of a messy task, because I'd have to solve for y and then take the derivative, and it has a bunch of square roots in it, and kind of ugly. But in this case, the polar equation's really easy to deal with. R equals 5. So the rectangular equation might be harder to deal with when you're dealing with calculus topics, and the polar equation might be easier, like in this case. On the other hand, if we're dealing in polar with a line versus dealing with that same line in rectangular, it might be easier to deal with it in the rectangular system than in the polar system. So in this one, the polar system's probably easier to deal with. In this one, the rectangular system's probably easier to deal with. Okay. So it's nice to go back and forth, nice to be able to go back and forth between systems and just pick which one's the easier to deal with. Which system's the easier to deal with. And that's basically the benefit of knowing these different systems, that we can pick and choose which ones are easiest to deal with when we want. Let's take a look at this one. We want to convert from rectangular to polar. This is actually a parabola. We have x squared is equal to 16y. We don't have x squared plus y squared. Adding a y squared here wouldn't be very helpful because we'd have to add it on both sides. We don't have a y over x, although we could try to make one. You could do that. So what I'd probably do is I would probably replace the x with r cosine theta and replace the y with r times the sine of theta. Since I have an r squared on one side and an r on the other, what I can do in this case is divide both sides by r. Oh, I'm sorry. So this is the equation. And now I'm going to try to solve for r. So I'm basically at this stage, and I'm going to solve for r. Here, I had to get the terms with the r on the same side and then factor out. Here, I'm going to solve for r using a different method. I'm going to divide both sides by r. And then I get r times cosine squared is equal to 16 times sine. And then I'm going to divide both sides by the cosine squared. You'll get r equals 16 times sine theta divided by cosine squared of theta. So I converted into polar, and then I solved each equation for r. Okay. Any questions about that? Pretty straightforward stuff, I hope. Again, the different techniques of solving for r, there's a number of different techniques you can use. I just showed you two of them. One is getting the terms on the same side with r's and then factoring out the r's. That was in the previous example. Oops. And then the other technique, I had to divide both sides by r's and then divide by the coefficient. That was in this example. So there's a lot of different techniques where you can solve for R. And I'm not going to go through all of those because there's just so many algebraic techniques. Instead, let's convert in the other direction. Let's go from polar to rectangular. And we'll start out with these two. R equals 4. Now, that's pretty easy to guess what we're going to do on R equals 4 because we already went from rectangular to polar and we had R equals 5. But there's a point I'm going to make, and that's why I didn't erase my circles from earlier. We're going theta equals 10 too. All right. So if I have something like R equals 4, probably the easiest technique on this one is to square both sides and then replace the R squared with X squared plus Y squared. And just like before, we get a circle, except now it's radius 4. 1, 2, 3, 4. I have that in blue. Okay. Theta equals 10. Well, I don't have a specific to get rid of theta, but I do have a specific thing to get tangent of theta. So I'm going to apply tangent to both sides. And then tangent can be replaced with y over x is equal to some number. Now in this case, tangent of 10 becomes 0.648 or about 0.65. Now, for purposes of what we're going to do in this class, when you convert into rectangular, you do not have to solve for y. So I'm just going to leave this one alone. But I'm going to make a point on this one. So on this one, I am, just for this example, just so I can make my point. Notice that y over x is equal to a number is the exact same thing as y is equal to that same number times x. So it's y is equal to slope times x. I get a linear equation that is through the origin. So I get a line through the origin. That means that every theta equals number is going to be a different line through the origin. Oftentimes, when you graph a polar, or if they look for a polar graph, you'll see a drawing that looks like this. The reason that your polar graph looks like that on the polar graphing paper is because those are R equals a number theta equals a number. When we have x equals a number and y equals a number in our rectangular coordinate system, well, all of the y equals a number, those are just horizontal lines. X equals a number are just vertical lines. And so the standard rectangular grid looks the way it does because those are x equals number, y equals number lines on the grid. The polar grid looks the way it does because that's r equals number and theta equals number lines or curves on this grid. That makes sense? So the polar grid looks that way. All right. And if you want, you could, for instance, go to something like Desmos. Do I have a polar grid on here? And switch your grid from rectangular to polar and kind of see what that looks like. So here's the polar grid that Desmos has. A bunch of circles of different radiuses and lines out of those lines through the origin. Okay. We will be graphing a little bit later. But I just did want to point that out. So the polar grid looks the way it does because those are our most, that's what we get with our most basic equations of r equals number, theta equals number. Okay. Now let's do some other conversions. These will be a little bit more interesting. Let's say we have r equals 7 times secant theta. Well, there's no conversion for secant. When I say that, I mean on these equations, on these 4 equations, I don't see a secant anywhere. We just have cosines and sines and tangents. So when you see something like secant, you want to convert that into 1 over cosine so that you can use it. Now 1 over cosine times 7 is 7 over cosine. And you can probably guess what I'm going to do here. I'm going to multiply both sides by cosine so that I get r times cosine of theta is equal to 7. And then I can replace the entire r cosine theta with an x. So r equals 7 secant theta. That's the vertical line x equals 7. Now, what if we have r equals 8 times sine of theta? It looks very similar to the previous one, but actually the solving technique is going to be very different. So we have sine theta. But when we want to convert it into rectangular, we need r with our sine theta. I can't divide by sine theta because I get r divided by sine theta. That's not the same thing as r times sine theta. So the trick in this one is to multiply both sides by r. And if I do that, I get r squared is equal to 8 times r times sine theta. Now, r sine theta can get replaced with a y because we know y equals r times sine theta. Remember, we're using our 4 equations. R times sine theta, we can replace that with a y. And here I have an r squared. And because I have an r squared, I can replace that with an x squared plus y squared. So I replace my r sine theta with a y and my r squared with x squared plus y squared. So by the way, that's going to be a circle. It will not be centered at the origin, but it will be a circle. Okay. It'll actually be centered at 0, 4, I believe. And what I do when I go from polar to rectangular, you don't need to convert this into y equals. In fact, it'd be very, very difficult to do so. So we're not going to convert that into a y equals. We're just going to leave it as is. And so if you're asked to convert polar to rectangular and you get something like this, then you stop here and plug this in. Notice that on these two different examples, I needed to get r cosine theta, or I needed to get r with the sine theta in order to exchange those things out. Okay, I can't really easily just exchange a cosine out. I need r with the cosine. I can't just exchange out a sine. I need the r with the sine. And there's different ways to get that r together with a cosine or a sine. Like in this one, I multiply both sides by cosine, that did it. In this one, I had to multiply both sides by r, that did it. Let's convert this polar equation into a rectangular equation. There is r equals 12 times tangent theta times secant theta. So I go back to my conversion equations. And I say there's nothing for secant, so let's change that into a cosine, 1 over cosine. But I do have a tangent, so I can kind of leave tangent alone. So that's what I'm going to do. Now, this is not the only way. You could have converted tangent into sine over cosine as well. But what I'm going to do is I'm going to leave tangent alone. And I'm going to call secant 1 over cosine. And then just like the previous example, I'm going to multiply both sides by cosine. That'll give me r cosine theta is equal to 12 times tangent theta. Now, again, look carefully at your conversion expressions. I don't need an r tangent theta. I just need tangent theta. Tangent theta can be replaced with y over x. And r cosine theta now can just be replaced with the x. Now, if you want to stop there, that's fine. You can stop there. But I'm going to just quickly multiply both sides by x so that you can see what this is. This is a parabola. And so if you were to graph this, you'd also graph and get a parabola. All right. Just like this is a circle centered at 0, 4. If you try to graph this, you're going to get a circle centered at 0, 4. Okay, of radius 4 too, by the way. So again, if we can get a tangent theta, if we can get r cosine theta, if we can get r sine theta, or if we can just get r by itself, or r squared, then we can make those substitutions from polar into rectangular. Okay. Sometimes that's easier said than done. Sometimes it's hard to see, what the quickest way to do the conversion is. Like in this one, it was fairly messy. Okay. Now, the last thing I want to do is I want to sketch some polar graphs. Like I said, usually when we're dealing with polar, we write our graphs like r equals a function of theta. R equals some expression with theta. And you can see 4 different versions of that down below. And we also have a couple of different versions written on the board right now. There's a number of ways you can sketch graphs. Option number 1 is just plug in different values for theta and figure out the corresponding r, and then plot a bunch of points around. Plot points and connect them. So I can just plug in a bunch of different values of theta into this. I know how this is going to work. So if I plug in a theta of 0, you get 0, and then you start plugging in, and you get a bunch of points. Oh, I didn't draw that very good. And you might get some points. And you might get all these points, and then you draw connect the dots, draw the graph, right? That's what you do on this. Another option would be convert to rectangular and recognize the graph. Or I should say, and just graph it there. Graph in rectangular, whichever way you want to graph. So in either of these, that would be fine. But let's say we wanted to do it here. I know r equals 12 tangent theta secant theta. I've already converted that into x squared equals 12 times y. And if I know that that's a parabola pointed up, going through the vertex, I can simply graph the parabola in the rectangular system. And now that's the same graph as in the polar system, right? Same graph either way. So if you wanted to do these two examples, either of those options would have been just fine. You could have plotted points, then connected the dots. You could have graphed in rectangular, things you've already know. But what we're going to do is we're just going to use technology in polar form to graph whatever we're trying to graph. All right. And I'm going to show you this both in Desmos and also with the TI-84 or TI-83 calculator. Okay. So these two we've already seen. So let's actually, we kind of know what we should get. So I'm going to graph these two in both Desmos and on the calculator. Actually, okay. So if we go into Desmos, it actually doesn't matter which grid you have. I'll just use my rectangular grid for right now to show you that it doesn't matter. But if you're willing to type in a polar equation, Desmos is going to recognize it. So the one we just looked at, r is equal to 8 times sine of theta. Now, in order to get the symbol theta, you just type in THETA. And as soon as you hit that A, it converts it to the symbol. Now, under here, you have to be a little bit careful. It says, what are the bounds on theta? So you could go from 0 to 2 pi. And again, to get pi, you just type in P and then I. Or if you only went from 0 to pi over 2, you're only going to get part of that circle. All right. So just make sure that your bounds are enough so that you get the whole picture that you're looking for. So play with those a little bit. But that's all I got to do. R is equal to 8 times sine theta. And we get that same picture that we just did. The other one we just had on the board, r equals 12 times tangent theta. Again, remember, make sure you write theta times secant of theta. theta. And sure enough, I get a parabola. Now, if I scroll out, looks like 0 to pi on this parabola is plenty in terms of being able to see the whole parabola. But sometimes you might have to adjust the theta. Okay. So here I went from 0 to 2 pi. So that's how you do it on Desmos. On the calculator, let me show you that. So here's my calculator. Typed in things. It turns out your calculator has a polar mode. So if I go into mode, scroll down, we've dealt with parametric mode before. Now we're going to be dealing with polar mode. And by the way, make sure, as always, we're dealing with radians. Otherwise, things are thrown off. But if you're dealing with polar mode, we're all set. Now you hit y equals. I don't want that plot on. And you'll notice that I get r equals an expression. If you type in 8 times sine theta, and by the way, to get the theta, you just hit this button right here that has the variable. So in polar mode, when you hit the variable key, it'll pop up as the variable theta. And then I'll zoom standard, I guess. And there you go, I get a circle. Now this looks a little bit elongated because my screen is a little bit longer than it is wide. This is a circle though. If you want it to look more like a circle and have proper so that your left and right measure the same units, then you use the zoom square. All right. That way, one tick on here, if it's like, if one tick in the XY direction is 3 millimeters, then one tick, if one tick in the X direction is 3 millimeters, then one tick in the Y direction is 3 millimeters. That's what square does. But you can graph any polar thing you want. 12 tangent of theta times secant of theta. Obviously, there's no secant button, but you can do 1 over cosine. And there you go. You get that parabola. Okay. And if you want to see more of it, obviously you can zoom out. There you go. So that's the idea of how to graph, either using your calculator or using Desmos. Now that we've seen that, I want you to kind of just plug these into your calculator and see what they look like. 3 plus 7 cosine theta, 5 minus 5 sine theta. And I'll plug some of these into Desmos and see what they look like too, because these are kind of interesting plots. And r equals 4 sine of 5 theta, r equals 3 times cosine of 4 theta. I'll try to, again, plug those into Desmos. But I want you to plug in a couple, and then I'll do some investigations. All right, so let me plug these into Desmos and see what they look like. Also, like I said, we can plug these into our calculator and see what they look like as well. So let's start with the very first one. That was 3 plus 7 times cosine theta. Again, if you're typing into Desmos, 3 plus, oops, hit the wrong button. 3 plus 7 cosine theta. Notice that I get this weird shape where we loop around and it has an outside and an inside loop. That's called a lemacon with an inner loop. Very interesting shape. How about if we do this? R equals 5 minus 5 times sine of theta. Well, in that case, I got a very similar shape, but I did not get an inside loop. It came up, kind of went to the origin or the pole, and then back around, touched the pole, back around. And the reason for that is the relationship between the number, the constant number, and the coefficient on our sine, or the constant number and the coefficient on our cosine. So let me show you what I mean by that. Let's say we start increasing that constant number. So 3 goes to 5. Notice how the inner loop got smaller. 5 goes to 6. That inner loop got smaller yet. Then it got to 7, and the inner loop went away. When that 7 goes to an 8, then it doesn't even get all the way back to the origin. And when the 8 goes to a 9, again, it doesn't go all the way back to the origin. It's kind of smoothing out. So the relationship between this number and this number tell you how much of a loop, if any, you have, or whether it hits the origin. If those two numbers are the same, then it hits the origin, just like we had with 5 and -5. If the constant is smaller, then we get an inner loop. If the constant is bigger, then the coefficient in front of the cosine then it doesn't even hit the origin. Okay. And the difference between that and 9 minus 7 is just the direction. So the positive negative aspect of this just flips it around, in this case, the y-axis. Because with cosine, we're oriented left and right. With sine, we're going to be oriented up and down. But it's the same thing. I go numbers smaller, I get a loop. The size of that loop depends on the size of the difference in these numbers. Once you hit 5 and 5 or 5 and -5, you hit the origin. Once you start getting bigger, you no longer come back to the origin. Okay. And again, if you do a minus versus a plus, it just points it in the opposite direction. And the same thing would be true if you did a negative sign in front of the 7. So the negative sign in front of the 7 doesn't change anything, but the negative sign in front of the 5 does. Changes the direction. Let's see if that's the same thing with cosine. With cosine, if you, whoops, change that to a plus, pointing to the right, minus pointing to the left. What happens if I do another minus? Well, that doesn't change anything on the minus sign on the 9. So you can see how these work, where we have number plus or minus a number times cosine, or number plus or minus number times sine. Let's do a couple other ones. And the other ones that I'm going to type in are the ones that were shown on the screen. So let's do 4 times the sine of 5 theta. Notice what we get. We get what looks like a flower with 5 petals. That's not a coincidence that that 5 in front of the theta gave rise to 5 petals. Now, just as a note, if you have a circle of radius 4, notice that this petal is going to be inscribed inside the circle of radius 4. That's because of this 4 as my coefficient of sine. So I get this 5 flowered petal. And again, if you change the 5 to a 3, you get 3 petals. If you change the 5 to a 7, you get 7 petals. 7 to a 9, you get 9 petals. But they're all inscribed in the circle of radius 4. Now, weirdly enough, that's the same thing if sine changes to cosine. You still get a flower with 9 petals, if I have a 9 there, or 5 petals if I have a 5 there. It's just oriented a little bit different. With cosine, one of the petals will be aligned on the polar axis. With sine, one of the petals will be aligned along the line theta equals pi over 2. Now, here's a weird thing that happens. If we change this number from an odd number to an even number, it turns out with an even number coefficient in front of the theta, the number of flower petals is actually double the number. So if I put a 2 in front of theta, I get 4 flower petals. If I put a 4 in front of theta, I get 8 flower petals. If I put a 6, I'd get 12 flower petals. So interestingly enough, we get these weird shapes that we see here. All right. And those aren't the only interesting shapes we have. We saw earlier that when we had 8 times sine theta, we got a circle centered on the y-axis. Well, if you do r equals 8 times cosine theta, you get a circle centered on the x-axis. Circle centered at the origin, we know should be r equals a number. There's also this thing called an Archimedean spiral. If you do r equals theta, now this r equals theta starts at theta equals 0, and it just spirals out. Interesting. These were the ones that I was talking about. R is equal to a plus or minus b times cosine theta, or r equals a plus or minus b times sine theta. Okay? You get an inner loop if the ratio between a and b is smaller than 1. You get exactly a cardioid, which means it goes back and touches the origin if the ratio between a and b is 1. You get dimpled if the ratio between a and b is between 1 and 2. And that dimple gets erased if the ratio between a and b is bigger than 2. I didn't show one of those, but that's what you get. Rose curves are also interesting graphs. We just saw those, where if you have an even number inside of the argument of cosine or inside of the argument of sine, you get double that many petals. If you have an odd number inside the argument, you get exactly that number of petals. And if it's cosine, one of your petals is going to be along the polar axis or the x-axis. And if it's sine, one of your petals is going to be along the y-axis, or the line theta equals pi over 2. And there's lots and lots of other really interesting looking polar graphs. Here are a few. So you can get some really neat looking patterns with these polar graphs. And I just want to say some of these neat looking patterns are great. Let's take the rose curve, for example. Trying to graph this in rectangular coordinate system would be very, very hard. Trying to graph something like that using X's and Y's is very, very hard. So it's nice to have these polar systems because they give us graphs that we would never see in a rectangular system. Okay. So not only are some things easier to deal with in polar, some things would be near impossible to deal with in rectangular. So polar is nice in certain situations. Polar is nicer than rectangular in certain situations. And then in some situations, using rectangular is basically impossible. So that's the end of this section on polar coordinates. Next class period, we will deal with some of the calculations with polar coordinates. And that's what we'll end on next class period. All right. So I'll see you then.